Hi, my name is Drew Dozer, and this is Lab 4. Some preliminary info. The purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. So the sum equations, we had the loop rule is 0 equals the sum of the differences in voltage. Capacitor voltage is V equals Q over C. Ohm's law, which is resistor voltage equals V equals IR, and then I equals the negative derivative of Q with respect to time. And then for the last bit in the calculations of RC, we use the delta V equals delta V naught, E times E to the negative T over RC, giving us that the natural log of delta V over delta V naught equals negative T over RC, which we can then use to calculate RC. Initial conditions, wires have no resistivity, and then systems and surroundings, circuit is system, everything else is surroundings. So for the main result preview, you can kind of see that we made this graph here, and we see that it rapidly increases from A to B, and then decreases from C to D and E to F. And then over here you can see that we found the slope of that line I just mentioned earlier to be negative 0.1668, which we then use to calculate RC to be about 5.995. The experiment description, the document was followed, and we set up several circuits in the PhET simulation and then analyzed several things such as current, voltage, and capacitor charge and discharge. The results are simply final steps in the experiment, so we'll walk through those two things together. So, in the first image here, you can see that the ammeter in the same direction as the current and in opposite direction of the current both read the same reading of 0.02. We estimated the current earlier to be 3 over 147, which is about 0.02, and we simulated it to be 0.02, so this is fantastic. For the second part, the readings on the voltmeter is 3 volts, indicating the change in the voltage between the regions in the circuit is all of the voltage. And the ammeter reads 0, which is how much current is currently running through the circuit. So unlike the ammeter, the voltmeter has an incredibly high resistance, so almost no current flows through the circuit because of this. And so the ammeter reads that no current, and the voltage drop across the voltmeter is all of the voltage, negative 3. With the red positive lead before the black one, we measured the voltage drop in each one element to batteries, negative 3, the top resistor, 0.96, lower resistor 2.04, ammeter 0, and wires 0. We measured the current as 0.02 amps. The sum of the expected is 0, and then we added those up and we got 0, and so the voltage drop is as expected. As you can see the graph here, it rapidly increased from A to B, then stayed constant from B to C, and then decreased to 2.4 from C to D, stayed constant from D to E, and then decreased to 0 from E to F, and then remained 0 throughout the rest of the circuit. The ammeter does not change in this first image because the voltmeter is wired in parallel and has an incredibly high resistance, causing it to have a negligible effect on current. But in the second image, the ammeters now read the current as if they were only the first resistor because they have such a little resistance, like that of a wire, that the electrons choose the easier path and flow entirely through them, basically ignoring the second resistor. We then calculated the resistances in each resistor to be around 48 ohms and around 102 ohms, and then of course wires and ammeters were both 0. So for the second experiment, we have the light gets bright, diminishes, and turns off in both situations. The current starts high, and then as the capacitor charges, it slows and stops. And then the current grew while the capacitor discharged, but then shrunk again as there was no new current provided to the circuit. The 10 ohm bulb, we calculated the charge of the capacitor to be 5.27 charging, 4.65 discharge, and the 20 ohm was 9.85 charging, 10.28 discharge. So then we calculated RC to be 5.995 using this graph and this slope of negative 0.1668. So yeah, the capacitor charges up to about 60% of its capacity in about 6 seconds. There were basically no sources of error. It was a very walked through simulation with it's a simulation, so not much could go wrong. Maybe the significant figures of RC were a little too few to produce an entirely accurate result. So for the first what if question, a real ammeter would not have zero resistance. So the current while the ammeter is attached would be less than simulated, as there's a greater resistance, and some electrons would still flow through the bigger resistor in the parallel ammeter step. Due to a lack of resistance, this is a second what if question now, the ideal model suggests the capacitor would fully charge instantly, indicating RC equals 0 because R would be 0. However, in the real world, wires do have some resistance, so this ideal model does not hold true. Thank you.